Well, I thought I'd take a minute and look at three little examples of partial fraction decomposition. In the first one you see here, we're not going to integrate this. We just want to look at the question and make sure that we can be certain of the nature or the form of the decomposition. And what I mean by that is, what would you do first in the problem if you were going to integrate it? So instead of integrating this, we want to break this up into separate functions of which we would integrate then each one. Now, in the denominator, we have a polynomial of degree 3 multiplied times a polynomial of degree 4 if you square this. So this ends up being a polynomial of degree 7. The numerator is a polynomial of degree 2, so this is what we consider proper form. That means that the degree of the numerator upstairs is bigger than the degree downstairs. Okay, so now for the nature of the decomposition, or what are the fractions going to look like? Well, we have a linear factor of multiplicity 3. Now the multiplicity 3 just means that it's going to appear 3 times. It's the same thing, x minus 1 times x minus 1 times x minus 1. The linear factor is x minus 1. And the rule is that in the fraction over here, you've got your linear factor, and the degree of the top, the numerator, must be exactly 1 smaller than the degree downstairs. So this is linear, so degree upstairs has got to be 1 smaller, which means it's degree 0, and degree 0 polynomials are constant. Then we'll have an x minus 1 squared. And again, what's important is that the linear factor is x minus 1, not the squared. Well, you might say, well, wait a minute, if you square that, it's a quadratic. So then this would have to be a polynomial of degree 1. No, that's not what we're talking about. What's important is the factor is linear. And then we'll have another term that's going to be c over x minus 1 cubed. So that takes care of this factor in the rational expression. Now, we have an irreducible quadratic. This cannot be factored over the set of real numbers. It can be factored, of course, over the set of complex numbers, but we don't study complex numbers in this course. So this is irreducible, sort of like a prime polynomial, kind of like a prime number. So we're going to have an x squared plus 7. And then in the numerator, what we must have is the most general polynomial that is exactly 1 degree smaller. Well, if this is degree 2, then this has to be the most general polynomial of degree 1, and that's going to have the form d times x plus e. So this is the most general form of a polynomial of degree 1. Okay, but then we see that this irreducible quadratic has multiplicity 2. It just means it appears twice. But the important thing is that this is an irreducible polynomial of degree 2. So that means we're going to have an x squared plus 7 squared. And then the numerator must be the most general polynomial again of degree 1. So that is the complete nature or form of the decomposition. Now, if we were going to continue the problem, we would find these coefficients a, b, c, d, and e, f, and g, and it would take us the rest of the weekend. This would be a challenging problem. But that's it. I just want you to make sure that you understand how to do these, how the nature of the decomposition would look like. Because if you begin with this incorrect It doesn't matter how good you're going to be at the integration or the mountain, in this case, of algebra that would follow. So I hope that helps a little bit. That's the end of problem 1. Okay, now for the second example. Let's work this one all the way through. So we're given this problem, and the first thing we do is we check to see if it's of the correct form, if it's proper. Downstairs, if you multiply everything together, you get a polynomial of degree 3. Upstairs, we have a polynomial of degree 2, so the degree upstairs is smaller than the degree downstairs. So it's a proper problem, a proper rational expression. So here we are. I've already begun this. Each linear factor, each factor in the denominator is linear. And notice that in this one, they only appear once, so there's no multiplicity, or I guess you could say each one has multiplicity 1. Therefore, each term is linear in the denominator, so the decomposition will be this nature here. So in class and in the textbook, what we would turn around and do is get a common denominator again, which is this, and get just a large expression and a lot of algebra. What I want to do is I want to suggest a compromise between the method in the book and the Heaviside cover-up technique. So this will have the same spirit as the technique in the book, but we're going to take advantage of the essence of the Heaviside method. So let's do this. Let's again, just like in the textbook, let us get a common denominator. Now the common denominator is always this. So now watch what I'm going to do. I'm going to skip a step and assume that we're going to get a common denominator. So we're going to end up with two fractions that are equal, and those two fractions have the same denominator, which forces the numerators to be equal, because the only way two fractions can be equal where the denominators are the same, then it must be the case that the numerators are the same. So I'm going to take this numerator now. If I'm going to look at this fraction and I'm going to get this denominator to look like this one, then I need to multiply by those two terms, because in this denominator those two terms are missing. So I'll end up with a times x plus 3 times the x minus 1. And similarly, for the middle term, I want to make x plus 3 look like this. So I would need to multiply top and bottom by the two that are missing, x and x minus 1. So I get b times x minus 1. And again, what we would have is x times x minus 1 divided by x times x minus 1, which is a fraction equivalent to 1. And then can you see what's going to happen on the last one? The last one will become c, and we're going to need an x, and we're going to need an x plus 3. So that's what the textbook does. And all I've done was taken a little shortcut. Down here in the denominator would be x times x plus 3 and x minus 1. And over here would be the same denominator. So let's just consider the numerators. Now, that's what the book does. And now let's use the essence of the Heaviside method. If you look up here, we have a denominator of x, a denominator of x plus 3, a denominator of x minus 1. Now I'm going to take this expression and I'm just going to look up here. When x is 0, this part is 0. So I'm going to come down here, and in this, remember, this acts essentially, and in fact it is, an identity. So I'm going to let x equal 0. And I'm just going to plug 0 in for x all the way across. Now over here, I'll get minus 9. And now what's going to happen? If I let x equals 0 in this term, I get minus 3a. Now here's the really cool part. If I let x equal 0 in this term, the whole thing is 0. Similarly, if I let x equal 0 in this term, the whole thing is 0. So look, I end up with just this. So clearly, a is 3. And I'm just going to put a note up here that a is 3. And I'm also going to put a note down here that a is 3. Okay, now I'm going to repeat this. I'm going to let x equal negative 3 in a second. And then I'm going to let x equal plus 1. So let's do that. Let x equal minus 3 everywhere. Now if x is minus 3, this is going to become 4 times 9. Minus 3 squared is 9. Plus 13 times minus 3 minus 9. So this is going to be 36 minus 39 minus 9. Well, this is negative 3 minus 3, so we get minus 12 equal. Now look what happens. If x is negative 3, this term is 0. And this term is 0. The only term that will not be 0 when x is negative 3 is this one. Now if x is negative 3 minus 1 is negative 4. Negative 4 times negative 3 is 12. And as pretty as you please, we see that b is minus 1. Okay, now let that sink in. So we've got the mechanics, if you want to say it, of what's in the book, but we have the cleverness of the Heaviside method. Now finally, let x equal 1. And remember, where I'm getting these numbers here, they're just the values of x that make that denominator 0. So if I let x equal 1 everywhere, I just get 4 plus 13 is 17. 17 minus 9 is 8. But look what happens. If I let x equal 1, this term and this term are 0. They're both 0. And we come over here, if we let x equal 1, we get 4 times 1. So we have 4c. So then c is 2. Isn't that good? That is very nice. So to work the problem, let's copy this all down one more time. Let's finish this and do the integration. So what I'm going to do is just integrate each term. So this is going to be equal to 3, the integral of 1 over x dx. We know that a is 3, so I'm factoring that out. Now we know b is minus 1, so this is minus the integral of 1 over x plus 3 dx. And then 2, the integral of 1 over x minus 1 dx. And that's it, folks. This is 3 natural log absolute value of x minus the natural log of x plus 3 plus 2 natural log x minus 1. And of course, the constant. And again, the way we get this, if you let u equal x plus 3, it becomes the integral of 1 over u. du is dx. So that's pretty cool. I like that. That's a good compromise. All right, here's the third problem we're going to look at in this video. And it's similar to the last ones, but we have a linear term with multiplicity. The numerator's a little more complex. It's a tougher problem, isn't it? This one's going to be a tougher problem. Now, let's look at the nature of the decomposition. And you can just pause the video and write this down and get caught up. So, we see that we have a linear factor of multiplicity 2, and then another linear factor multiplicity 1. So let's consider the term that's linear with multiplicity 2. Now the term is linear, so we're going to have a over x plus 1 and then b over x plus 1 squared, and that takes care of this term. The last term will just be c over x minus 5. Okay, and when we do notice that the degree downstairs would be 3, the degree upstairs is 2, so it is a proper rational expression. So we are good to go. So let's get a common denominator. This will reduce to 2x squared minus 25x minus 33. Now all you want to do is make this denominator x plus 1 look like this. So you would have to multiply top and bottom by another x plus 1, and then you would have to multiply top and bottom of the fraction by x minus 5. Since we're only looking at the numerators, this is going to be a times x plus 1 times the x minus 5 term. Now for b, if I want the denominator in b, the middle term, if I want this denominator to look like this one, I simply need a x minus 5 factor. And then for c, we need c times x plus 1 squared, because that's what's missing in this denominator if we compare it to this. So make sure you understand that. First of all, what's really important is to make sure you've got the correct form for the decomposition, and then this part here. And again, we would have the denominator under each part. So I'm only looking at the numerators once we get a common denominator. So let's proceed. I'm going to let x equal minus 1 everywhere, because see, this is an identity. It is an identity. Okay, if we let x equal minus 1, what's going to happen on the left? Well, minus 1 squared is 1, so this is a 2. So this would be 2 plus negative 1 times negative 25 is plus 25, and then we have minus 33. So that's 27, positive 27 minus 33, so we're going to end up with a minus 6. Now what happens on the right when x is negative 1? Well, this term is 0, isn't it? Because that's 0. Negative 1 plus 1 is 0. That term's gone. This term's gone. The c term is gone. All we're left is with the middle term. Now if x is negative 1, negative 1 minus 5 is minus 6. And guess what? b is equal to 1. As easy as that. There's not much in it. Now, let's let x equal 5. Okay, it's going to be a little arithmetic over here. 5 squared is 25 times 2. So I get 50. Now, 5 times minus 25 is minus 125. And then we have minus 33. Well, boy, this is going to be minus 158. So minus 158 plus 50. So this is going to be minus 108, I hope. Now what's going to happen on the right side over here? If I let x equal 5, this term is 0. And this term is 0. So I'm only left with this term. Remember, x is 5, so 5 and 1 is 6. 6 squared is 36. And now that gives me c is minus 3. Just as pretty as you please right there. That could not be better. Well, there's an issue, isn't it? we have to find the coefficient a, but we've already used everything we can to get zeros up here. Well, remember, this is an identity, and by the way, so is this. So, since it's an identity, I can pick any number I wish to plug in for x, except -1 and 5. I've already used those. If I want to, I can let x equal 12, and I will get the value of a. If I want to, I can let x equal -44, if I was nuts, and I would get the value of a, and it would be the same answer. So see, since it's an identity, if I pick and plug in a number for x up here, or down here, as long as it's not one I've used, I will end up with what a equals. And it doesn't matter what I pick, except -1 and 5. Well, let's let x equal 0. Since it doesn't matter, I'm going to make life easy on myself. Over here, if x is 0, then that's -33. How about that? Okay, now you're letting x equal 0 everywhere. And remember, b is 1 and c is -3. Don't forget that. Now, if we let x equal 0, this is 1 and this is -5. So we get -5a. Let's do that again. I'm letting x equal 0 on the left, -33. And on the right now, if x is 0, that's 1, that's -5. The product is -5, so I have -5a. What's going to happen here? If x is 0, this is going to be -5 times b, but remember b is 1. So this is just -5. And finally, the last term, if x is 0, this is 1 squared, which is 1. So I get 1 times c, but c is -3. So we have -33 is equal to -5a minus 8. Add 8 to both sides. We get -25 is equal to -5a. So how about that? A is 5. Now, if you'd have come over here and if you had decided to let x equal 2, for instance, this equation would have been different, but you would have still gotten the value of 5 for a. A equals 5 regardless of what you plug in for x here, knowing the values of b and c. That's why I say it's an identity. Since it didn't matter, I made life easy on myself by picking the 0. Now we're ready to do the integration. So the original problem, now that's going to equal what happens when we integrate each piece here. So factor the 5 out, so we have the integral of 1 over x plus 1 dx. Don't you forget that dx now. Plus then the integral of 1 over x plus 1 squared, minus 3 then the integral of 1 over x minus 5 dx. Okay, now I hope it's clear that when you integrate this first term, you get 5 natural log absolute value of x plus 1. And when you integrate the last term, you're going to get -3 natural log of x minus 5 in absolute values. But what's this term? Ooh, I forgot the dx. Here I am, fussed at y'all, and I forgot it. How did we do the middle term? Okay, well, let's work it right down here. No one's watching. We'll do it right here. This is 1 over x plus 1 squared dx. I'm just going to use substitution. If I let u equal x plus 1, this becomes the integral of u to the minus 2. See that? And then du is just dx. Now, when we integrate, we get u to the minus 1 over minus 1. So it's a negative 1 over u. So the middle term, when we integrate this, it's going to be a minus 1 over u, but u is x plus 1. And then plus c. Wow, what a problem. Okay.